In previous lecture, we studied for Landau level and Landau quantum oscillation behavior. And quantum oscillation by the electrical resistivity measurement, we call it is a Cherenkov-de Haas oscillation, and the magnetization oscillation, it is the de Haas-Van Alphen oscillation. And and here I will describe for the experimental analysis on the quantum oscillation, and the detailed quantum oscillation analysis was done by the Lifshitz and Kosevich formula. Therefore, then we call it is a Lifshitz and Kosevich is founded that the quantum oscillation theory. And here I did not mention the detailed theoretical calculation, but I'll just review the result, the calculation result, and how to analyze the data. And by measuring the quantum oscillation of magnetization, the magnetization represented like this, and it is that here the first factor is the oscillating amplitude, and A is the oscillation amplitude, and the sign this factor is that 2 pi RF means that the oscillation frequency F is the oscillation Gauss-Van Alphen frequency, and beta is the phase factor. And here, by estimating the frequency by the fast Fourier transform, and we can obtain that the frequency of the quantum oscillation, and this frequency is directly related to the extremal orbit of the Landau level and Landau tube. And here, then here the Lifshitz Kosevich formula deals with the amplitude of the quantum oscillation, and the amplitude of quantum oscillation A proportional to the square root magnetic field, and also partial second derivative of Fermi surface with momentum with a perpendicular direction of a magnetic field. And this term is small for cylindrical Fermi surface, and also giving rise large oscillation for the pancake-like Fermi surface, and also small oscillation. And therefore, here we do not know in detail in this term, but here it is the other factor included, RT, RD, and RS. From the analysis of the amplitude analysis, we can estimate that various physical factors, and let me see in more detail. And here, then at first, we do not know the detailed calculation second derivative of S with the KH, but here we can see that RT is that the formula of the RT is like this. Here alpha is a parameter like given by this one is like Planck is 2 pi square CKB over EH bar, and the value is 14.7 Tesla per Kelvin. And also effective mass is proportional, or is written like h bar square over 2 pi partial SF and partial E, and this is the effective mass. And here RT is that hyperbolic sine alpha m star t over b, and therefore this RT value can be written like this. It is proportional to this formula. And here by measuring the amplitude of quantum oscillation, and this is a temperature dependent. The left figure shows that the temperature dependent de Haas-Van Alphen amplitude, and this amplitude can be fit with like this plot. And here the vertical axis is that 1 minus exponential minus 2 alpha m star t over b over t, and at n value, log value, versus the temperature is the versus temperature, then it shows that the linear shape and the linear estimation, and here we can be, the alpha is the value, and the magnetic field and temperature is parameter for external parameter, and therefore by making this kind of plot, the slope we can from the slope we can estimate that the effective mass. And here it is RT means that it is a temperature dependent damping factor, and from the temperature dependent damping factor, and by using this amplitude plot, then we can estimate that the effective mass, cyclotron effective mass of carrier. And secondly, second one is that the Dingle temperature, and the Dingle damping factor can be write down as the exponential minus alpha m star Td over B. Yes, Td is the Dingle temperature, and also alpha is the constant, and the m star is given calculated from the temperature dependent factor, RT factor, and therefore, this kind of Dingle temperature can be estimated by the analysis on this plot. And also here, the Hertz-Banach amplitude with magnetic field. And previous one is the Hertz-Banach amplitude with respect to the temperature, and the temperature damping factor gives the effective mass of carrier, and also ILD is the damping factor, and the Dingle damping factor is that the Hertz-Banach amplitude versus magnetic field. Then in the plot can be like this, and the plot is that because the Hertz-Banach or the Cherenkov-Dugas quantum oscillation amplitude is proportional to the b to the minus 1/2, and the exponential, and divide by the hyperbolic sign value, and also therefore, and here ln a square root b hyperbolic sign this value, then it is a constant minus alpha m star Td over b. Therefore, and when we plot in the vertical axis like this, and the horizontal direction is the inverse B, inverse magnetic field. Then by this plot, and the linear inverse linear shape can be a linear line can be appeared, and also from this slope estimation, slope is that the minus alpha m star Td, and from this one, and T m star is obtained from the temperature damping factor, and also here Td can be estimated from this one, and therefore Td, then Dingle temperature is related to the relaxation scattering rate. 1 of tau is the scattering rate, and also h bar 2 pi kb are constant. Therefore the Td Dingle temperature is related to the scattering rate. And therefore, then here by using this relation, then by estimating that the Dingle temperature, and we can calculate the relaxation time, and by using the relaxation time, we can calculate the mean prepass of carrier. And here, this is a mean prepass can be given by the Dingle temperature and effective mass, and also therefore from this calculation we can from the Dingle damping factor, then the Hertz-Banach amplitude versus magnetic field plot, this plot can be obtained for the mean prepass or the scattering time. And also finally, in the RS means the spin damping factor. Spin damping factor is the cosine of this value, and it is oscillating parameter. And anyway, this G is that the lambda G factor, and the R is that the harmonic number, and this value, this oscillating amplitude vanish for spin zeros, like 2 R m star over mg. M0 is the 1.2 n. Then it is a minimum value, zero value of the quantum oscillation. And also from this one we can calculate effective mass, we already know the effective mass, and the integer n is that the number of the oscillating period, and therefore the g can be, lambda g factor can be estimated from this spin damping factor. And we can calculate the spin lambda g factor from the theoretical calculation, and also the experimental plot on this experimental investigation can estimate that the experimental lambda g factor. Therefore, we can compare with each other. This is one example for the quantum oscillation, the Haas-Van Alphen effect. And we measure the magnetization versus magnetic field, and it shows that quantum oscillation, and we subtracted the background, and also the magnetization fluctuation versus inverse magnetic field shows that this kind of fluctuation. And by using the fast Fourier transform, and we can make that this kind of several peaks corresponding to the several frequency. And this frequency is that quantum oscillation frequency, and therefore it is related to the extremal orbit of the Landau level, Landau sheets, Landau tube. Therefore, from this estimation, we can estimate that the extremal value of the Landau tube. And therefore also, then this kind of, we can measure the various temperature dependent value, and here we measure from the 0.5 Kelvin step at various temperature measurements from the 0.5 to the 1 Kelvin step, and we measure various isothermal magnetic resistance. And then for example, alpha pocket, tau, kappa, delta, alpha pocket has amplitude, has a temperature dependence, and this fast Fourier transform amplitude decreases like this, and this value, the line is the Lifshitz Kosevich formula fit, and which corresponds to the, we can estimate that the effective mass of carriers for each corresponding Fermi pocket. And therefore here we do, and as a further, we can estimate that the Dingle temperature or a Dingle relaxation rate, relaxation time, or the mean prepass like that. And this oscillation amplitude has much information on the various physical parameters such as the effective mass, or the relaxation time, or the mean prepass, and so on. Yeah, it is very good. It is very fruitful to investigating the experimental quantum oscillation.